This is the projected trajectory of munitions consumption in a high-intensity Pacific conflict. War games consistently show the United States exhausting its critical inventories within the first week. The flat line represents our current defense industrial base. It is built for precision, not the sudden, massive volume required by a peer war. This production ceiling is a byproduct of the exquisite model that has defined U.S. strategy for decades. We have optimized our forces around a small number of incredibly capable systems, like the F-35 fighter. But these platforms are inherently difficult to replace. Their requirements are so specialized that they rely on bespoke labor, closed software, and brittle supply chains. You cannot simply build more of them on short notice. While the commercial sector underwent a massive revolution in hyper-scalable, automated manufacturing, the defense industry remained largely siloed. Commercial giants can output complex electronics by the millions, but that efficiency has yet to take root in weapons production. Surviving a large-scale conflict requires closing this gap. It means shifting focus from maintaining exquisite stockpiles to mastering the process of rapid industrial conversion. Industrial conversion is the active repurposing of massive civilian manufacturing sectors, like automotive or tech, to meet sudden wartime requirements. In a pure conflict, victory is less about the weapons sitting in a warehouse today and more about the structural capacity of the commercial economy to build them tomorrow. We have a century of data showing that this transition is never seamless. The American experience in World War II provides the blueprint for the structural hurdles we face today and the specific levers required to move them. During the defense period of the early 1940s, military planners operated under a dangerous assumption. They believed civilian factories could simply swap from cars to tanks overnight. This chart captures the resulting reality. The blue bar represents the military's 1941 estimate of what was feasible. The red bars show the actual scheduled expenditures. There was a massive, persistent gap between what the military needed and what the economy was willing to provide. Automakers resisted conversion because defense contracts required massive upfront investments and specialized tooling, equipment that would have zero value in the post-war commercial market. It took until 1943 for actual production to finally align with those early targets. This is the first bottleneck. In peacetime, corporate financial incentives naturally conflict with the needs of national defense. A factory making profitable consumer goods has little reason to stop production for a risky military contract. The solution was the War Production Board. Under Donald Nelson, the government stopped negotiating and started regulating, assuming the authority to prioritize the war effort over the civilian market. This timeline of defense expenditures shows the impact. Production only scaled after the board instituted mandatory curtailments on commercial vehicles and centralized the allocation of raw materials like steel. Notice the slope of the line after Pearl Harbor. Once the government used its authority to force market compliance, the output curve went exponential. By late 1942, 95% of the auto industry had transitioned to war work. History shows that when commercial profit and national defense compete for the same resources, defense loses. Without a centralized authority to mandate compliance, voluntary industrial conversion remains a theory rather than a reality. Even with government authority, a second bottleneck emerged: the sheer complexity of military hardware. An M4 Sherman tank is a fundamentally different machine than a civilian car. Rapid battlefield feedback led to constant design changes. Every time the military updated a specification, the mass production lines in Detroit ground to a halt as machines were retooled, creating a friction between design evolution and manufacturing scale. This friction is still with us. Today, the Pentagon is in high-level talks with giants like General Motors and Ford to ramp up weapons production. But modern assembly lines are even more rigid than those of the 1940s. They are highly optimized, automated environments designed for a singular, stable purpose. We are facing the same bottlenecks. In the 1940s, the challenge was retooling physical gears. Today, the challenge is rerouting proprietary software and digital supply chains. When the military introduces exquisite requirements or shift specifications midstream, it breaks these commercial systems. Design complexity causes the same critical jams in a digital supply chain that a physical part change caused in 1942. Simply throwing contracts at automakers won't solve the capacity crisis. The weapons themselves have to be redesigned so their software and physical components can actually be built at scale. Strategists are now proposing a 21st century architecture for this transition, the Civil Reserve Manufacturing Network. The DoD acts as an integration hub, connecting military needs to a reserve of commercial factories. First, it identifies simple items commercial giants can easily mass produce. Second, commercial firms act as subcontractors, filling critical gaps for defense primes building complex platforms. Third, it partners with tech innovators to rapidly adapt emerging commercial technology for the battlefield. And fourth, it leverages contract manufacturers who specialize in building other people's designs, allowing for a rapid surge in physical output. To be effective, the infrastructure and legal protocols for this network must be established and tested before a conflict begins. Building the regulatory framework in peacetime removes the friction of legal and financial negotiation, which history identifies as the primary barrier to immediate surge capacity. But the weapons must also change. Technology alone cannot force production if the digital architecture of the weapon is closed and bespoke. This is why concepts like Anduril's Lattice and their Arsenal factory are significant. They treat weapons as modular, software-defined systems. Open architectures break complex systems into standard commercial subcomponents. Because software governs the interfaces, hardware can be built in any standard factory. This departs from the legacy model, where closed proprietary architectures forced the military into narrow, slow-moving production lines. Achieving this surge capacity requires a shift in priorities. We must accept attritable systems, cheaper, expendable weapons that prioritize volume and flow over individual perfection. In a peer conflict, production is a flow rate problem. We can no longer rely on a narrow pipe of high-value items. We need a wide pipe capable of delivering high-volume systems by the tens of thousands. Today, the bottleneck isn't just raw steel. It is the digital architecture that locks a weapon into a single factory or opens it up to the entire economy. Solving the crisis requires these three pillars: peacetime policy to align markets, open software to enable modularity, and physical integration with the commercial sector. The United States will always need high-end, exquisite capabilities, but combining those advanced platforms with the mass production capacity of the commercial sector creates a scale of deterrence that exquisite systems alone cannot match. True national defense readiness is not measured by the size of the weapons stockpile we hold, but by the exponential scaling capacity we engineer into the commercial economy for tomorrow.